In addition to being the sponsor of this Zoom call, Jim also arranged our speaker. So I will ask Jim now to do the introduction of Mike Clancy.
Thank you, Brooks. It's pretty easy to introduce Mike because a lot of you already know him, for one thing. If one back in the early days of Mike's employment locally, I'll talk about it, had decided what to do to deal with climate change, he practically did that. He has a degree in oceanography and meteorology, both of which are absolutely fundamental to dealing with the climate change. He has a very good understanding from his experience with chemistry, physics, analytical methods, everything if you want to put together a package of education for climate change, he has it. He has a total of 28 years experience with the Fleet Numerical Organization in Monterey. He, at the final 6 years of that experience, he was pretty much head of the place. He was the director of science and technology. He had a $27 million annual budget. He had a capital investment of $120 million he was managing. He had a very responsible job, and for which he got many awards, some over 50 awards, including the highest Navy civilian award. So he comes with tremendous credentials. Time to turn it over to him. Thank you.
That wonderful. Let's see, I guess I'm okay. Can everybody hear me? I hope. Thanks so much, Jim, for that wonderful introduction. And I want to also thank Brooks and David Thon for helping set this thing up. I know this is the inaugural Zoom meeting for this group, so hopefully, you know, it'll go well. I'm happy to be the guinea pig here. I'm going to start by sharing my screen, and we're going to be looking at a lot of slides here. So I'm going to probably be on slides pretty much most of the talk, but at the very end, we'll come back for questions, and hopefully we'll have plenty of time for questions. Now, you may see on the right-hand side of your screen, obscuring part of the slides, sort of a matrix of three or four pictures of people. If you hover your mouse at the very top of that, you'll see some icons, and the icon to the far left, if you click that, it'll minimize those pictures. And then you'll be able to see the slides a lot better. So the title today is Climate Change, Causes, Consequences, and Solutions. Here's a quick outline of what we're going to talk about. Introduction and context, going to be a lot of science embedded in that. Then talking about the greenhouse effect, greenhouse gases, global warming projections for the end of this century. Where are we going? What are the consequences of that warming and climate change? What are the solutions we need to be pursuing to mitigate climate change? And finally, I'll have some closing comments. Well, I want to begin by showing you this graph, which is a depiction of global mean surface temperature of the Earth going from the present time back 5 million years. Now, let's make sure we understand what we're looking at here. Global mean implies averaged over the entire face of the Earth, pole to pole, all around the Earth. Surface temperature over the ocean means the sea surface temperature. Over the land, it actually means the temperature a few meters above the surface, over the land and over the ice. Where did this information come from? Well, it comes from proxy data. Proxy data often involves things like isotopic analysis of various elements that are found in ocean sediments or ice cores, things of that nature. And what you see is about 2.5 million years ago, at the beginning of what we call the Pleistocene epoch, about 2.5 million years ago, the Earth began experiencing ice age cycles. Now, technically, these are called, the warm spikes here are called interglacial periods, and the downward excursions are called glacial periods, but I'm going to use the popular term ice age to depict these glacial periods. I'm going to refer to this climate change as the ice age cycle. So about 2.5 million years ago to about 1 million years ago, the Earth was experiencing a 40,000 year ice age cycle. And for about the past 1 million years, the Earth has been experiencing a 100,000 year ice age cycle. So why am I talking about ice ages? We're here to talk about climate. Well, the fact of the matter is, for the last couple of million years, the ice age cycle has dominated natural climate change. And we need to understand that, because the climate change we're concerned with is happening against a backdrop of this natural climate change. So we need to understand what is driving the ice age cycle. The ice age cycle is still in effect today. And how does that pertain to the global warming we're concerned with? So the question on the table is, do we understand the ice age cycle? Do we understand what drives this? And the answer is absolutely we do. In fact, we've understood it for about 100 years. The ice age cycle is driven by variations in the Earth's orbit around the sun and in variations in the orientation of the Earth in space. That's what drives the ice age cycle. Now, I'm sure you know that the Earth orbits the sun in an ellipse, which is kind of a drawn out circle. But what you may not know is this ellipse is not constant in time. It actually varies on a 100,000 year period due to the gravitational force of Jupiter and Saturn acting on the Earth. Now, this figure is exaggerated here, so you can see it. It's actually about a 1% variation here, but that's enough variation to have a significant impact on climate. This is called the eccentricity cycle. And I'm also sure that you know that the Earth is inclined, and the axis of the Earth is inclined relative to the plane that the Earth orbits in. That's, of course, what gives us the seasons. In Northern Hemisphere summer, the North Pole is tilted towards the sun. And in Northern Hemisphere winter, it's tilted away from the sun. But what you may not know is that that tilt is not constant in time. The Earth rocks back and forth from a maximum of about 24.5 degrees tilt to a minimum of 22.5 degrees, about 2 degrees variation there on a 41,000 year cycle. And that's caused by the gravitational force of the sun and the moon acting on the Earth. Now, I'm also sure you know that there's a North Star, and that North Star happens to be called Polaris. The North Pole points towards that North Star Polaris. But what you may not know is that the Earth wobbles on a 27,000 year period, again caused by the gravitational force of the sun and the moon acting on the Earth, such that about 13.5 thousand years from now, the star Vega will be the North Star, not the star Polaris. Now, we've understood these cycles for about 100 years. They're called, collectively, they're referred to as the Milankovitch cycles. You may hear that term. It's named after Serbian astronomer and geophysicist Milutin Milankovitch. He discovered this and wrote about it, published his work back in the 1920s. Now, how does that drive the ice age cycle? Well, it works like this. When these orbital variations conspire to produce decreasing solar radiation striking the Earth during the Northern Hemisphere summer, that takes the Earth into an ice age. Now, that cooling effect, taking into the ice age, is amplified by three important feedback effects here. The first is called the snow ice feedback, and it works like this. Decreasing sunlight absorbed by land and sea yields decreasing global temperatures, which means increasing snow and ice, which reflects more sun back out, solar radiation back out to space, which amplifies the cooling. And you go around this feedback loop and it amplifies the cooling. Similarly, decreasing global temperatures yield a cooling ocean, decreasing evaporation of water from the oceans and land. That yields decreasing water vapor in the atmosphere. Turns out that water vapor is a strong greenhouse gas, so that's yields less trapping of long wave radiation, which further decreases global temperatures. And again, you go around this feedback loop like that, and it amplifies the cooling. And there's also a CO2 feedback loop here that involves CO2 being released or absorbed in the biosphere and the ocean. And that produces a transition to the ice age. Now, it works the other way around. When these orbital variations conspire to increase solar radiation striking the Earth during Northern Hemisphere summer, you go around these feedback loops in the opposite direction. So I'll just talk about this one. Increasing sunlight absorbed by land and sea yields increasing global temperatures, decreasing snow and ice as the snow and ice is melting. And you get a similar effect on the water vapor loop here too. That amplifies the warming and you come out of the ice age. Now, why am I talking about Northern Hemisphere summer? Why isn't it Southern Hemisphere summer? Why is it Northern Hemisphere summer so important? Well, that's because the northern hemisphere has a lot more land than the southern hemisphere, so there's a lot more snow on the ground. That's part of it. But also at the North Pole, there's an Arctic Ocean. At the South Pole, there's a Antarctica. And the Arctic Ocean, when the ice melts, it leaves behind dark ocean, dark seawater, and that absorbs much more sunlight than the ice does. And so that actually allows the snow ice feedback loop to operate much more strongly in the northern hemisphere than in the southern hemisphere. So that's why the amount of solar radiation striking the Earth during the northern hemisphere is the key issue here. So that's what drives the ice age cycle. You can see that for the last million years or so, the eccentricity cycle, that Earth becoming, the orbit of the Earth becoming less like a circle, more like an ellipse, has been driving the ice age cycle. And I'm going to zoom in here now. I'm going to take another look here. We're going to look way over here. This is the 5 million year look. Now we're going to take a look way over here, right about this kind of sliver of the chart here. Here we look at it. And it's showing, again, the same parameter, global mean surface temperature of the Earth, but now looking back 22,000 years. And what you see here is the last ice age. This minimum to the left of the screen there is the last ice age. And we see the recovery from the ice age, which takes about 10,000 years. For the last million years or so, this 100,000 year cycle, it kind of works like this. We're in the ice age for about 60,000 years. It takes about 10,000 years to come out of it. We're in what's called the warm period, interglacial period here for about 20,000 years, and then another 10,000 years to transition to the next ice age. So what we see here is recovery from the last ice age driven by eccentricity cycle. That means the Earth was becoming, orbit was becoming less like an ellipse, more like a circle. So in northern hemisphere summer, the Earth was moving closer to the sun. That was a warming effect. But over the last 7,000 years or so, we see this slow cooling trend headed towards the next ice age. And that, in fact, is driven by the obliquity cycle. What that means is over the last 12,000 years or so, the Earth has lost about 1/2 degree of angular tilt. As that rocking back and forth occurs, the Earth is losing tilt, and that has produced a cooling trend. Now, there's a couple of other identifiable features visible here. This about a 1,500 year interruption in the warming and recovery from the ice age is called the Younger and Older Dryas period. Dryas comes from the name of a flower. It's Dryas octopetala. It's a 8-petaled flower which flourished in Europe during this time, during this temperature range, and it's found in sediments, and so they give it that name. This was caused by a disruption of the ocean's thermohaline circulation. The overturning circulation of the ocean affected the Gulf Stream, and that disruption of the thermohaline circulation was caused by all of the fresh water that was being transported to the ocean as the glaciers melted, as the Earth warmed and the glaciers that covered the land melted. That causes interruption, but the orbit of the Earth became more and more like a circle, and more solar radiation in northern hemisphere summer. It overcame that, and we continue to warm. You may have heard of the medieval warm period. That's this little bump right here. This is back during the period of castles and knights. Oh, by the way, for point of reference, human civilization began right about here, about 9,000 years ago. So everything we know about the human experience occurred during this period right here, which is called the Holocene interglacial period. This is the medieval warm period. We understand what caused that. The sun actually was burning brighter during that period. There was a maximum in sunspot activity. There was a minimum in volcanic activity, which actually produced a warming effect. So we got this little bump here called the medieval warm period. This is called the Little Ice Age. This happened during Elizabethan England, about a 200-year period where the Earth was a little bit cooler than normal. It wasn't an ice age at all. That's just a popular term, but it was referred to as a Little Ice Age. And during this period, most famously, the River Thames froze over. And again, the sun played a role in that. And in fact, this was a period of enhanced volcanic activity. Volcanoes release aerosols into the atmosphere, which reflect solar radiation away from the Earth, and that cools the Earth. And then finally, we come to this red spike. This, in fact, is the post-industrial global warming that we are concerned with. Now, there's a couple of things that are obvious when you take a look at this. The first thing is this red spike, this warming, is going in the wrong direction. The natural climate change here is we should be cooling. We have been cooling for thousands of years. We should continue to be cooling for the next about 8,000 years at about this pace, at which point the transition to the next ice age would begin, and the next ice age would happen in about 18,000 years from now under normal conditions. But in fact, the temperature is going in the wrong direction. The second thing is it's going really fast. In fact, this temperature spike here is going about 20 times faster than natural climate change. This is natural climate change. This is what we've been experiencing for about the last century. 20 times too fast in the wrong direction. So what does 20 times too fast in the wrong direction mean? Well, let's say you're a golfer and you're golfing at Quail Lodge, and unfortunately you take a wrong turn in your golf cart, and suddenly you find yourself westbound on Carmel Valley Road, puttering along at 10 miles an hour. Unfortunately, it's car week, and suddenly you encounter a Lamborghini going the other way, 200 miles an hour. Well, that's the difference between natural climate change and what's happening now. If natural climate change is the golf cart, then what we've been experiencing for the last century is the Lamborghini going 200 miles an hour. It's not natural climate change. So we're going to zoom in now on this red spike. Take a closer look at it. So we're again looking at global mean surface temperature of the Earth, the same thing we've been looking at all along. But now we're going back to 1850 to 2017, and we're looking at this parameter, global mean surface temperature of the Earth, from 5 different sources: the Japanese Meteorological Agency, European Center for Medium Range Weather Forecast, the United Kingdom Meteorological Office, NASA, and NOAA. Now, each of these products is independent and different. Some of them involve computer models and satellite data and other data. Some of them don't involve any computer models. Some of them don't involve satellite data. Some only involve surface data. So 5 independent analyses, 5 different approaches towards handling data, 5 different data sets, and they all basically depict the same picture. And that picture is as follows. From 1850 to 1880, not too much happening. From 1880 to 1910, slight decline. From 1910 to 1945, pretty strong upward movement. From 45 to 75, slight decline. And then beginning in the mid-70s, rapid upward climb of temperature. Now, a couple of other things to notice here. First of all, there's a very high level of agreement between these 5 independent groups here, particularly in the modern era since the 70s. And that gives us a lot of confidence in this product, the fact that 5 independent groups come to the same conclusion. It also shows us that we really have a good handle on the temperature of the Earth. We have the temperature of the Earth is very well sampled by the observations we have out there. The other thing to note here is it doesn't go up in a straight line. It's kind of like the stock market, right? It doesn't go up in a straight line. There's volatility here. We call these spikes, this volatility here, climate variability. Climate variability is caused by things like El Nino, La Nina, the Pacific multi-decadal oscillation. There's a whole slew of these kinds of phenomena, usually involve the ocean and the atmosphere interacting together. They cause changes here that typically occur on timescales of months to decades. Climate change is happening on a longer timescale, 30 years or longer. When you're talking about climate change, you need to be looking at records that are 30 years or longer. If you're looking at records that are from a couple of months to 20 years, you're clearly looking at climate variability. You're not looking at climate change. If you're looking at the latest storm that hits Washington, you're looking at weather. There's weather, climate variability, and climate change. Climate change is this long-term trend here. These up and down spikes is climate variability. And if we looked at the daily stuff, we'd see lots of variability happening. That's weather, but we're really concerned about climate change here. Now I'm going to show an animation of one of these products, and that's going to be the NASA product. And what we're going to be looking at here is going to be temperature anomaly, global temperature anomaly. A temperature anomaly is just a fancy way of saying temperature difference from a reference field. The reference field in this case is going to be, for every place on the Earth, is going to be the average from 1951 to 1980, a 30-year average. And the scale over here is shown here. Where you see white depicted on the chart, that means a zero anomaly. It means the value is the same as that 1951 to 1980 average. Where you see yellows and oranges, it's warmer. Dark oranges means 2 degrees centigrade warmer. Where it's blue, it's cooler. Dark blues mean 2 degrees C cooler. Now, a couple things about the data on this. This is based on only in situ data. There's no satellite data involved here. If you're worried about satellite data, forget it. There's no satellite data. There's no computer models in this data set. You don't like computer models? Don't worry about it. No computer models here, only in situ data. That's data that's taken in place. And it's a lot of data. Over the ocean, about 350 million observations. Over the land, several billion observations from all the meteorological stations around the world. Now, you may have heard about the urban heat island effect. That's a real effect whereby the temperature is anomalously warm in cities because all the concrete and buildings trapping the heat. Don't worry about it. The urban heat island effect is not present in what I'm going to show you. About 200 stations were deemed to be contaminated by urban heat island effect, and they have been taken out of this analysis. So no urban heat island effect here. You may be aware that in the first half of the 20th century, ocean temperatures, sea surface temperatures were measured by throwing a bucket over the side, reeling it back in, sticking a thermometer in. Those are called bucket temperatures. Beginning about the middle of the 20th century, there was a transition to engine room injection temperatures. That means the temperature of the sea surface was measured by down in the engine room by a thermometer that was embedded in the injection port of the water coming in to cool the engine. Why is that important? Well, there's a bias there. The bucket temperatures were known to be biased by cold by about 1/10 of a degree centigrade, because when you pull the bucket up, you know, the water would evaporate, would cool, and that kind of thing. And on the other side of the coin, the engine room injection temperatures are known to be biased warm by about 2/10 of a degree centigrade, because the engine room is hot. As the water comes in there, it's warm slightly. Why is that important? Well, that's a big bias you have to worry about. That'd be like 3/10 of a degree centigrade bias. Well, don't worry about it. It's been all corrected out very carefully. Those biases have been corrected out based on what type of observation is in there. So having said all of that, I'm now going to run this animation, and I'm going to call out the decades. You don't worry about the numbers that are going to be changing out here. I'm going to call that out. Keep your eye on what's happening around the world here, and pay particular attention to what happens in the 1970s. As we recall from the previous graph, that's when things really take off. So here we go. I'm going to call out the decades. Here we are in the 1880s, 1890s, 1900s, 1910s, 1920s, 1930s, 1940s, 1950s, 1960s. Here come the 70s, 1970s. Now watch what happens. 1980s, 1990s, 2000s, 2010s, and end up with 2018. So let's draw a couple conclusions here. A couple of things are pretty obvious. The first is the land is warming faster than the sea. In fact, it's warming about twice as fast, although the sea is warming, that's for sure. You see all these yellows around the world ocean. It turns out about 95% of the heat of global warming is actually going into the ocean, but yet the ocean's warming only at about half the rate of the land. That's because the oceans have very, very high heat capacity, about 100 times the heat capacity of the land. That heat capacity is how much heat you have to add in to raise the temperature by a degree. And the oceans have huge heat capacity, partly because water has a very high specific heat compared to air and soil, but also because the heat in the ocean is mixed down to great depths, ultimately down to the bottom of the ocean over long time scales, but almost instantaneously down to the depth of the ocean mix layer, which is typically about 20 meters to 100 meters deep. So the ocean is absorbing the vast amount of the heat, but it's actually warming up slower than the land. The land is, the farther north you go, the more the land warms. The tropics are not warming that much, but as you go farther north, particularly the North Pole, it's really warming a lot. It's warming about 2 to 3 times faster as you go northward. That's a direct result of that snow ice feedback we talked about before, and the fact that there's an Arctic Ocean up here. And that's not good news, because we have the Greenland ice sheet here, which is melting at an increasing rate. That's contributing significantly to sea level rise. All the mountain glaciers are melting, contributing to sea level rise. Same thing is happening to a degree in Antarctica, so that's a big problem. Notice the continental United States. The western third is warming significantly more than the eastern 2/3. If you live down in Florida, you haven't really experienced that much global warming, but if you live in the western states, you've experienced a lot. You've seen the area get much warmer, and you've seen it get much drier. I can tell you in Monterey County over this period of time, Monterey County has warmed about 1.9 degrees centigrade. The global temperature has gone up about 1 degree centigrade, but Monterey County has warmed almost twice that, 1.9 degrees centigrade. So that's an important thing. And then the final point I want to make is it's not warming everywhere. Notice that there are some blue patches here. There's a big blue patch just south of Greenland, and there's some blue patches in the Pacific Ocean, blue patches along the Antarctica. It's not warming everywhere. And these blue patches are mainly caused by changes in ocean circulation. The Gulf Stream circulation has changed here. There have been changes, important changes in the Antarctic circumpolar current. As the climate changes, the ocean circulation changes, and that can lead to areas where there is cooling. So that's why you really need to think about global warming as being indeed a global phenomenon. So what's going on here? What's causing all this? Well, it is in fact the greenhouse effect. And to talk about the greenhouse effect, we need to first understand the Earth's energy budget. And the Earth's energy budget is depicted on this graph here. And the numbers here reflect flows of energy in watts per square meter, flows of heat in watts per square meter. And these numbers are averaged over the entire face of the Earth over actually a 7-year period, day and night, all 4 seasons. So it's a global average overall, averaged in that way. And what you see is energy coming in from the sun, about 340 watts per square meter. Some of it is reflected by clouds and aerosols, goes out, does not warm the Earth. Some is reflected from the surface, particularly from snow and ice, goes out, does not warm the Earth. And some, of course, is absorbed by the Earth. It does warm the Earth. Some is absorbed by the atmosphere. The surface of the Earth is also cooled by what's called the sensible heat flux, the latent heat flux, which involves evaporation. There's latent heat released in the atmosphere and clouds. And then finally, the Earth is cooled through infrared radiation or long wave radiation. We refer to often as the solar radiation as short wave radiation, and the infrared radiation as long wave radiation. Long wave radiation is emitted from the tops of clouds, from the surface. It's affected by greenhouse gases, and it cools the Earth. Here are the greenhouse gases, and that is water vapor, carbon dioxide, methane, nitrous oxide, and the F gases, or the fluorinated gases. Now, the greenhouse effect works like this. Incoming solar radiation warms the Earth. Reflected solar radiation over here and outgoing long wave radiation cool the Earth. Greenhouse gases, the ones we talked about, trap outgoing long wave radiation and warm the lower atmosphere and the surface of the Earth. And human activities increase greenhouse gases in the atmosphere and increase the warming. Now, in addition, that warming is amplified by those feedback effects we talked about before. Particularly, we talked about the snow ice feedback. Increasing global temperatures yields decreasing snow and ice. Increasing sunlight absorbed by land and sea, you can kind of see it here. The ice is white and it reflects the sun. When it melts, it leaves behind a much darker ocean, which absorbs the sun, and that basically amplifies the warming. What happens is the reflected radiation from the surface goes down here, and this number goes up, and that amplifies the warming. It's also amplified by the water vapor feedback we talked about briefly. Increasing global temperatures yields increasing evaporation of water from oceans and land, increasing water vapor in the atmosphere, which amplifies the warming, and that causes this number to go up here and that number to go down there. Now, this is not just me saying all this. There is in fact a overwhelming global scientific consensus on this matter. And this is just a partial list of leading science organizations around the world that confirm human-induced global warming, including the 3 most prestigious science organizations in the US. That's the US National Academy of Sciences, the US National Research Council, the American Association for the Advancement of Science, as well as the 2 organizations in the US that have purview over the atmosphere and the ocean. That would be the American Meteorological Society and the American Geophysical Union, and the list just goes on and on. There's an overwhelming international scientific consensus on this matter. The science is settled, and indeed it has been settled for many years. So let's talk about these greenhouse gases. Now, notice when I showed this figure before, I colored water vapor. This is water vapors, carbon dioxide, methane, nitrous oxide, and the fluorinated gases. I color the water vapor differently. That's because water vapor, although it amplifies global warming through that water vapor feedback loop we talked about, it does not drive global warming. And that's because humans are not putting water vapor into the atmosphere. In fact, water vapor, which we perceive as humidity, is in balance with the natural hydrologic cycle. And it's increasing only in the sense that as the natural hydrologic cycle increases because the ocean is warming, it nudges the water vapor in the atmosphere to a higher level. It amplifies the warming through that feedback effect, but it does not drive global warming. It is these anthropogenic greenhouse gases here that drive global warming. We humans are putting lots of these gases into the atmosphere, and they are not in balance with any natural cycle. Water vapor is in balance with the natural hydrologic cycle, but the anthropogenic gases are not in balance with any cycle. As a result, they're increasing steadily. Now let's take a look at that. So here are the anthropogenic greenhouse gases, and they're put in order of how much they're contributing to the current rate of global warming. Now this is a snapshot in time. It doesn't take into account how the lifetime of these gases. It takes into account only two things: the potency of the gas and how much of the gas is in the atmosphere right now. And from that, you can determine how much they are contributing to the current rate of global warming. But from this, you see that, in fact, CO2, carbon dioxide, is the dominant contributor to the current rate of warming, followed by methane. The interesting thing here about this, I should mention in passing, is as you go down this table, these numbers go down, but the actual potency of the gas goes up. In fact, the fluorinated gases, these are gases that are used in refrigeration. They're used in some manufacture of semiconductors. They're used as electrical insulators. They are extremely potent, thousands of times more potent than carbon dioxide. But fortunately, there isn't much of them in the atmosphere. We really need to keep them that way. That's a very important issue. So let's take a look at CO2 in the atmosphere. As we've seen there, CO2 is the dominant gas that's contributing to the current rate of warming. So this graph shows a plot of CO2 in the atmosphere from 1700 to 2019. Now, CO2 levels are usually reported as parts per million, concentration in parts per million. The pre-industrial levels were about 280 parts per million, and we've recently surpassed 413 parts per million, which is an increase of almost 50% above the pre-industrial level. You can see things really took off beginning in about the 1960s here. The total mass of CO2 in the atmosphere is also of interest. Over this time period, we humans emitted about 2 trillion tons of CO2, not billion, 2 trillion tons of CO2 into the atmosphere. And of that, about 1.1 trillion tons are still there. We've put about 1.1 trillion tons. We are about 1.1 trillion tons above the pre-industrial level. And we're currently emitting CO2 at the rate of about 40 billion tons per year, not million, billion, 40 billion tons per year. You may hear the term Keeling curve. That's named after an oceanographer by the name of Charles Keeling. He was at Scripps Institution of Oceanography down in San Diego, and he was the first to make very detailed measurements of CO2 in the atmosphere. Made those measurements at Mauna Loa in Hawaii. Those measurements continue today. He's the first to determine that there was actually a seasonal cycle in CO2. Sometimes you'll see the Keeling curve depicted as a sort of a single line. Sometimes you'll see it kind of a sawtooth line. When you see the sawtooth line, that means they're showing the annual cycle. If you see it as kind of a straight line, then they've averaged out the annual cycle. That's what's going on there. So where's that CO2 coming from? Well, it turns out in terms of these are global greenhouse gas emissions by economic sector. And it turns out that the top 3 sectors account for about 3/4 of the greenhouse gases put in the atmosphere. And that would be electricity and heat production, number 1. That's basically energizing the power grid, all the burning of coal and oil and so forth to energize the power grid. The second, close behind, is agriculture, forestry, and other land use. That would include lamb and beef production, and most importantly, deforestation. And the third one is industrial production, particularly steel and cement production, which is actually releases large amounts of CO2 into the atmosphere. Next on the list is transportation. It's pretty far down. It's actually only 14%. You might think it would be higher. I think for the US, it is higher, but this is the global picture here. And there are a lot of places in the world where there aren't a lot of cars, or people drive very small cars. So it's actually pretty small. And that includes planes and ships and all of that. Fossil fuel production, that would be petroleum refineries, about 10%. And finally, on-site fossil fuel burning in buildings and homes. That would be heating and cooking with natural gas. So by country, who are the top emitters? Well, this is for year 2013, but I think the relative positions here are pretty close to being the same now. On the left-hand side of this chart, we're looking at total annual emissions in billions of tons of CO2. Very clearly, China is number one. Back in 2013, they were emitting about 10 billion tons. That's about a quarter of the world's emissions from China. United States is pretty close by, number two, well, down by a factor of 2, followed by all the countries of the European Union, and the list goes down from there. Another way of looking at this is per capita emission. So per capita emission, you simply take the number of tons that a country emits and divide by the number of people in the country. Well, there's a lot of people in China, so China drops pretty far down. United States, and that metric becomes number one. Our per capita carbon footprint is about 17 tons per person per year. So we're number one in this metric, but there are other countries that are pretty close behind us. Canada is up there quite a bit, and Saudi Arabia is up there quite a bit, and Australia is up there quite a bit. By the way, I forgot to mention, if you want to ask a question, please do so, and I'll stop and address it. We will have time for questions at the end, but if there's something you just can't figure out and are not clear about, or you have a burning question, please do stop me, and I'll even go back if you want to look at the other earlier slides. So that's where the CO2 is coming from. Where's it going? Well, about 30% of the CO2 emitted every year is going into the soil. It's getting sequestered into the soil, and that's great. That's what we want, mainly through trees and plants and so forth, and that's what we really want. About 20% of it is being absorbed in the ocean, and that's not so good, because what's happening is the CO2 concentration in the ocean is going up and up. That's contributing to ocean acidification you might have heard about. The CO2 combines with water to produce H2CO3, which is carbonic acid. Now, the ocean is on the basic side of neutral. I'm taking you back to your high school chemistry here. There's a pH scale, and 7 is neutral. Higher is more on the basic side. The ocean is actually kind of in the 8 range, so it is still on the basic side, but it's trending towards more the acidic side. And that's a real problem for the larvae of shellfish. They have a hard time forming their shells, as just a small change in pH can make it hard for them to form shells. It's also damaging to coral reefs. We're worrying about coral bleaching. Combination of warming oceans and ocean acidification is causing our coral reefs to die out, which is a huge problem. So about 30% in the soil, that's good. 20% into the ocean, not so good. And finally, the remaining 50% is accumulating in the atmosphere. And that's why that Keeling curve is showing that CO2 going up and up. So here is where we are now in this 22,000 year view, about 1 degree above pre-industrial level. Where are we going? Well, it depends on what we do. It depends on what we the people of the earth do. If we follow the most stringent recommendation of the Paris Climate Accord, which is basically to bring greenhouse gas emissions to or reduce CO2 emissions by a factor of roughly 3 between now and 2050. So reduce greenhouse CO2 emissions by a factor of about 3 between now and 2050, 30 years from now. And then continue reducing them to pretty close to 0 by the end of this century. We can hold global warming to this level right here by the end of this century. That would be 1.5 degrees C plus or minus 0.7 degrees C, right about here. On the other end of the spectrum, if we don't do anything, if we continue on what's usually referred to as business as usual, which means we basically throw up our hands and say, we're not going to do any of this stuff, just drill baby drill and burn baby burn, this is where we're going, way up here. 4.5 degrees C plus or minus 1 degree C. Now think about it. Look how extreme this is compared to where we've been. The entire human civilization has been in this blue zone right here and until just the last 100 years or so. The climate has been extremely stable, and now suddenly we're going way up here. Well, I don't think we're actually going to go way up there. I think we're going to probably end up somewhere in the middle, probably right about here. But still, that's pretty darn extreme. I can tell you right now, we're not on track to get to here. We're falling behind. So we're not going to achieve that goal of 1.5. But hopefully we're going up here. We're probably going to be somewhere in the middle, and that is pretty extreme when you see it in the context of this 22,000 year view. So what are the consequences of that? Well, the BBC produced a really nice video of talking about the climate change consequences in 2019. It runs a couple minutes here. I'm going to play that for you now.
What do we know about the impact of climate change on the world's weather this year? Let's start in the Arctic. Summer 2019 has seen Arctic ice 30% below normal. This region is heating up about twice the average of the rest of the world and is caught in what scientists call a positive feedback loop. That's where sea ice thins and melts, opening up vast expanses of dark ocean that absorbs more heat from the sun, causing further warming. This dramatic warming of the Arctic may affect the strength and position of the jet stream, which brings the weather to the likes of North America and Europe. Globally, July 2019 was the hottest month ever recorded, and the Northern Hemisphere had the hottest summer on record. France and the UK were just two of the many European countries to see their temperature record broken. Studies showed the heat wave in France was made at least 5 times more likely by climate change. July was also Alaska's hottest month in recorded history. Wildfires there and elsewhere in the Arctic Circle are estimated to have released 50 megatons of CO2 in just 1 month, the equivalent of Sweden's annual carbon output. Wildfires hit the UK too, but in February, temperatures reached over 20 Celsius for the first time ever in winter. And on the other side of the world, Australia saw its hottest January on record, prompting health warnings and total fire bans. But by the laws of physics, a warmer world could hold more water vapor and potentially lead to more severe rainfall events. While the link between climate change and the Indian monsoon is uncertain, Mumbai has seen record summer monsoon rainfall totals. Iran suffered devastating floods in the spring of this year, as exceptional rainfall followed a prolonged period of drought. In Africa, Cyclone Idai was described by the UN as one of the worst natural disasters ever to hit the southern hemisphere. Heavy rain and coastal flooding led to the deaths of more than 700 people. Storms like these are expected to become stronger in a warming world. And in September, Hurricane Dorian became the second most powerful Atlantic hurricane in recorded history. Gusts of 220 miles per hour were measured in the Bahamas. An estimated 35 inches of rain fell together with a huge storm surge. Sea level rise is already threatening other island communities, such as the Maldives. The Paris Agreement aims to pursue efforts to limit the global temperature rise to 1.5 degrees Celsius. But even under that scenario, sea level could rise by up to 77 centimetres by the end of this century. So 2019 has seen many examples of extreme weather that scientists predict could become the new norm in a warming world.
Okay, we'll take a little bit closer look at consequences. I like to divide the consequences into 2 categories. Natural consequences, that's consequences to the natural world, and human consequences. And I won't necessarily talk about all of these, but generally speaking, increasing temperature of the land, ocean, and lower troposphere. This is important to understand. Global warming is warming the lower atmosphere, and the upper atmosphere is actually cooling. Lower troposphere is about half the altitude where you are flying at in a jet airliner, surface to about 20,000 feet. That's where the warming is occurring. Everywhere above that, the atmosphere is actually cooling. And that is making the atmosphere more unstable. And that is producing an increasing frequency and intensity of severe storms. Also increasing frequency of life-threatening heat waves. There's an increase in the absolute humidity, water content of the air, and the speaker was just referring to that on that video. And that's fueling increasing frequency and intensity of floods in wet regions, but there's also a decreasing relative humidity, at least over land, which decreases the likelihood of precipitation. What this means is in dry areas, like where we live, there will be an increasing frequency of droughts and wildfires. The Western United States has been getting progressively warmer and drier. We've seen that here locally, more prevalence of wildfires. We can expect that trend to continue. Also decreasing snowfall relative to rainfall, which means decreasing snowpacks and earlier snow melt. Big problem for us here in California, since a lot of our water supply in the summertime comes from the snowpack. Melting of ice sheets and glaciers, which yields rising sea levels. We talked about the ocean acidification. There's also decreasing oxygen levels in the ocean. Taken together, these increase the mortality of coral reefs, that's coral bleaching. Even the Great Barrier Reef, which is the world's largest living structure, is actually under severe threat. Decreasing productivity of fisheries, increasing species migrations and extinction. So lots of impacts in the natural world. I want to actually highlight two of them in a little more detail. The first is the impact on the weather. What we're looking at here are trends from 1980 to 2010 in severe storms in green, severe floods in blue, heat waves, droughts, and wildfires in this yellow color. And what you can see here is the heavy lines here are trend lines. What you can see is since 1980, the trend is clearly going up. Severe storms, severe floods, heat waves, droughts, and wildfires. Clearly, the long-term trend is upward, and we can attribute that to climate change. The other thing I want to talk about is sea level. What we're looking at here is global mean sea level from 1900 to 2015. And this part here, which is highlighted in blue, is derived from tide gauge data. Tide gauge, of course, is a device that measures the tides on a daily basis. There's a tide gauge attached to the wharf in Monterey. If you average out the tides, you get a depiction over a long period of time of sea level rise. And what you can see is very clearly the sea level has been rising since 1900. The curve right here is derived from satellite altimetry data. There are a number of satellite, beginning about the 1990s, there are at any given time about 3 satellites in orbit that measure the sea level using something called satellite altimetry. And they agree pretty well with the tide gauge data, and they also show the sea level increasing. Important thing to note here, it is increasing, or the sea level rise is, the rate of sea level rise is increasing. Sea level is rising at an increasing rate, and it's continuing to accelerate, such that from 1900 to the current time, sea level has risen about 8 inches. And we're kind of on track to, by the end of the century, to be about 1 meter global sea level rise. Could be much higher though. Typically what's happened in the past is the computer models have underestimated how fast the sea level has been rising and had to been revised upward. Human consequences. Well, increasing economic costs resulting from increasing frequency and intensity of damaging weather events, increasing prevalence of wildfires and rising sea levels are going to cost countries. We're going to have to deal with those costs. Increasing competition among nations for water and food caused by increasing drought and decreasing agricultural and fisheries production. Increasing threat of disease as tropical diseases spread into higher latitudes. The outbreak of Zika virus in Florida a couple of years ago is a good example of that. Increasing displacements of people and unrest in populations susceptible to recruitment by violent extremist groups caused by increasing drought, floods, extreme weather, and sea level rise. Here's a good rule of thumb. A 1 meter rise in sea level, which is what we're on track for conservatively by the end of this century, will displace about 100 million people worldwide, about 100 million people, 30 million in Bangladesh alone. A 2 meter rise in sea level, which is within the realm of possibility by the end of this century, would displace about 200 million people. Now that's a recipe for disaster. Where are these people going to go? Where are the people in Bangladesh going to go? They got no place to go. Increasing human mortality from heat waves, other severe weather events, starvation, disease, and war. And these risks are unevenly distributed between groups of people and between regions. Risks are generally greater for disadvantaged people living in developing countries. That's because they generally tend to be low ground kind of countries that, not very far above sea level or on low ground. So what are we going to do about this? What are the solutions? Well, I highly recommend Project Drawdown. They have a website, drawdown.org. We'll take a quick look at it here in a second. Project Drawdown is a nonprofit organization that proposes, analyzes, and ranks solutions for reducing greenhouse gases in the atmosphere with the goal of reaching drawdown, the point in time when the concentration of greenhouse gases begins to decline on a year-to-year basis. It was founded in 2014 by noted environmentalist Paul Hawken. They produced 80 solutions for reducing greenhouse gases by avoiding emissions and or by sequestering carbon dioxide or already in the atmosphere. These solutions consist of technologies, practices, and policies organized into 9 sectors and implemented in 2 scenarios. Basically, they've produced a roadmap for the governments of the world to deal with climate change. I think they've done a great job. It's for real. I've looked a lot at what they've done. They've got a lot of brainpower behind this. And the great thing about it is they've not only proposed these solutions, they've really done a good analysis of what they're going to cost and what their benefits will be. So let's take a further look. These are the 9 project drawdown sectors: electricity, food and agriculture, industry, transportation, buildings, health and education, land sinks, coastal and ocean sinks, and engineered sinks. I'm going to encourage you to visit their website and explore around a little bit, and you'll see some interesting stuff there. Now, there's a cost associated with this. I mentioned there are 2 different scenarios, 2 different drawdown scenarios. Scenario 1 is hold global warming to 2 degrees centigrade by the end of the century, and that's a Paris Climate Accord goal. And the more stringent goal is to hold global warming to 1.5 degrees C by the end of the century. And Drawdown has done a good job of pricing that out. The 30-year cost to the world to achieve the scenario 1 is about $23 trillion. Not billion, trillion, $23 trillion, which is about 1% of global GDP. And scenario 2, which is the more ambitious goal, is a cost of about 30 trillion, about 1.25% of global GDP. But the kicker here is there's a return on investment. There's a significant cost savings, 95 trillion in the case of scenario 1 and 145 trillion in the case of scenario 2. Now, if these costs were apportioned out in proportion to GDP, the US portion of that would amount to, for scenario 1, about 190 billion per year. For scenario 2, about 250 billion per year. To put that in perspective, this is about half the defense budget right here. It's a big number, but when you look down here at the subsidies that are given to the fossil fuel industry. Now, the issue of subsidies to the fossil fuel industry are somewhat controversial. If you talk to the oil industry, they're going to tell you that it's a very small number. If you talk to environmentalists, they're going to say it's a very big number. The number I chose to show here is from the IMF, the International Monetary Fund. I believe they are a fair arbiter. And they conclude that the fossil fuel industry in the US is subsidized to the amount of about $650 billion per year. Now, does the US hand the fossil fuel industry a check for $650 billion a year? No, that doesn't happen that way. The way it works is there are tax subsidies deeply embedded in the tax code, have been for decades, that give huge tax breaks to the oil, or I should say the fossil fuel industry. Some of the richest companies in the world. So if one were to just simply reduce those subsidies by a factor of 2, it'd still be very substantial. That would free up enough money to really make the investments we need to address this problem. Well, I want to make some closing comments here, and then we'll open it up for questions. What actions can you take as an individual to deal with this problem of climate change? Well, you can learn the basics of the science behind why our planet is warming and the climate is changing. And by suffering through my talk today, you've taken a big step in that direction. You can do what you can to reduce your carbon footprint while still living the life you want to live. You can join an advocacy group, such as the Citizens Climate Lobby, CCL, and participate actively. And I'll tell you, there is an active Monterey chapter of CCL, and we'd love to have you join. Whenever you have an opportunity to interact with a leader in your community, be they political or otherwise, let them know that you want to see action taken on this issue. Become a leader in your community in this issue. I know a lot of you already are leaders, and you can use your leadership skills and positions to help bring about change on this issue. And last but not least, vote for candidates who will address your concerns about climate change. Okay, I'm going to now stop the share here and should appear on the screen and open up to questions.
Mike, you see
Pretty scary presentation. Thank you.
Yes. Do you see much of a turnaround in public opinion? I mean, we're seeing a very sharp turnaround, apparently, in, say, our racial attitudes. Are we seeing anything like that on climate change?
Yeah, it's actually been very encouraging. I have a couple slides on that. I'm not going to necessarily go try to find them, but yeah, what we're seeing is, attitudes are definitely changing. Roughly speaking, I think the numbers I remember, 10 years ago, only, 40% of the U.S. population understood that climate change was serious and was being caused by man. Now it's in the 60 to 70% range. I think there's an upper bound, but I think we're getting up there. There's certainly been significant movement in that direction. There is a significant climate denial movement out there, funded by the fossil fuel industry. I actually gave a separate presentation on that a while back to the OLLI group. So there is a very vigorous climate denial world out there, and very analogous to the efforts of the tobacco industry in the 60s and 70s to deny the harmful effects of tobacco. In fact, some of the same PR firms have been involved in both, but it's dying out. It just says the tobacco industry issues eventually got figured out by everybody, and the same thing is happening in climate change.
Mike, this is George Lockwood. The ocean, as you indicated, has absorbed an awful lot of carbon dioxide, but the language of the of climate change people really deals only with the atmosphere. But if we were to reduce the amount of carbon in the atmosphere, we also need to reduce the amount of carbon in the ocean, because the kinetics of the reaction are very rapidly in both directions.
Absolutely right. And the good news here is that as we reduce the CO2 in the atmosphere, the CO2 in the ocean will also start to reduce. What's causing it to be a problem now is because the overlying atmosphere has such a high concentration of CO2. As we bring it back down eventually to pre-industrial levels, then that CO2 will be given up by the ocean over a period of time. It'll take a long time, but at least it'll trend in that direction. The good thing about the ocean, the good side is it's absorbing all this heat, so it's kind of mediating, the warming. It's absorbing this heat, and it's keeping it, from warming as much we otherwise would see. The bad news on that is, as we try to cool the planet back down, all that heat will eventually be given back up by the ocean, and it's going to make it, more difficult for us to cool the planet down. It's mediating the warming that's happening now, but it's going to be mediating the cooling that's happening later when we try to cool the planet down.
Well, one of my concerns is there's a big push for carbon sequestration. In fact, Bill Gates is spending a lot of money in that area.
Yes.
But the amount of carbon dioxide we're going to have to remove from the atmosphere, as I read these figures, doesn't include the oceans either, or doesn't include the oceans. So it's going to be a lot more than what they're claiming. Is that correct?
That is correct. We talked about, about 20% of the emissions are going to the ocean, about 50% are going to the atmosphere. So there's more going to the atmosphere than the ocean, but the CO2 in the ocean is significant. And I don't think there's been any technologies proposed that would remove CO2 from the ocean. I think we just have to rely on the natural process, such that as we reduce CO2 in the atmosphere, there'll be a natural flow of CO2 out of the oceans.
Well, I myself, I think this is an area that's being ignored. There's a lot we can do to remove it from the ocean, but it's not in currently. This is not in our common current. People don't talk about it.
Yeah. Yeah, I agree. And there's a lot of talk about carbon sequestration that's going on, and that's good. But I think the big push though really needs to be to make the transition to green energy, getting away from burning fossil fuels in the first place, and making the transitions to green technologies.
Well, also agriculture. Agriculture is the second biggest contributor, and
Absolutely.
beef is one of the biggest in agriculture.
Absolutely.
We got to get off eating.
Yeah, beef, lamb, and dairy are huge, and it's actually about at least an order of magnitude difference. From a sort of a plant-based diet to the typical Western meat and dairy oriented diet, it's about a factor of 10 difference in greenhouse gas footprint. And unfortunately, what's happening as the developing world gets, richer, they want to be more like us. And they want to more adapt our diet, whereas in fact, we should be adapting their diet. So that's a big problem. Beef and lamb production and dairy are huge sources of greenhouse gas. The other big problem is the way agriculture is done. There's a lot of recommendations from Project Drawdown is to go towards a less intrusive agricultural, more natural agriculture as opposed to heavily tilling and heavily fertilizing the soil. This heavy fertilization and heavy tilling releases nitrous oxide into the atmosphere, and that's one of the more powerful greenhouse gases.
Well, my calculations show that eating one meal of oysters, 40-gram protein meal of oysters, eliminates the equivalent of 285 meals of beef.
I can believe it.
That's a startling figure.
Yeah, the food is a big part of it. It's a big part of the drawdown sectors there, food. And one thing I like to talk about is, we talked about the average American's carbon footprint is 17 tons. Well, you can reduce that 17 tons by 2 tons by just doing the following 3 things. Number 1, throw away less food. We Americans throw away too much food. Number 2, shift more to a plant-based diet, which means eat less beef, eat less lamb. And number 3, you want to eat local. You don't want, if you're going to eat a lobster, you don't want to eat a lobster that grew up in Maine, and had to be flown all the way across the country. You want to eat a lobster that was caught here in California. So just doing those 3 things can reduce your carbon footprint with regard to food by about 2 tons per year. I think
somebody else wants.
George, can I ask a question?
Sure, go ahead, Jim.
Is the current shutdown because of the virus a lab experiment that can tell us anything about the maybe short-term effects if we start cutting travel pollution and so on? Is there any good news there?
Yeah, I actually did an invited 15-minute presentation on that, which Dave knows very well, for the World Affairs Council. And the title of the talk was, "Is there a silver lining in the COVID, issue because of the, impact on greenhouse gases?" And my conclusion in the end was, unfortunately not. What we've seen is a pretty significant decline, about 7%. I think it's about 7% decline in CO2 emissions. And there's been a lot of nice stories about, pollution levels have come down and we can see the mountains we couldn't see before. That's all great. But the reduction has been about 7%. And that's really kind of a drop in the bucket compared to where we need to go. But the real concern is that it's going to bounce back pretty fast. Right now, there's a glut of very cheap oil on the market. There are actually oil tankers that are parked off ports in LA that are filled with oil because they've got no place to put them. And my fear, and I think it's going to be true, is that when countries are scrambling to revive their economies and put people back to work, they're going to view that cheap oil as a quick and simple way to to get the economies revived again. So I think you're going to see the fossil fuel use zoom right back up. That's exactly what happened in 2008. The 2008 recession brought down global emissions significantly, but 2 years later they bounced up, well above where they left off. So that's a real concern. The good news side would be, well, as we rebuild, maybe we can rebuild on the green side, and they're trying to do that in Europe. But of course, there are political forces that take you back in the other direction. So the bottom line is the amount that has come down is pretty small, 7%. And in the long term, I'm not optimistic about it.
I have a question about the dairy. You mentioned cows and lamb. What about sheep and goat? Is it the cows that are causing the problem, or is it the process of making the cheese? I guess is my question.
It's mainly the cows. They produce a lot of methane. There's a lot of greenhouse gases associated with raising cows and processing the meat and all of that. I don't have a graphic readily handy, but you can find some really nice graphics that show as a function of different types of food, you know, the greenhouse the carbon footprint.
So I'm eating sheep cheese and goat cheese, which I do a lot. I'm not contributing it.
They're pretty far down the list. Yeah, they're pretty far down the list. Yeah, it's really the meat is the big problem.
Okay.
How about, Mike, how about sequestration technology where they're trying to capture carbon? George mentioned it with Bill Gates before. Does
Yeah.
it look like it's economic? Can it be done in volume?
Yeah, there a few years ago they passed a law which was really trying to address that, and they've put into part of that law is to build out a pipeline infrastructure to capture that CO2 and actually inject it down into the ground, and that has some promise. But you know, I'm not terribly optimistic about that. Part of it, you know, it passed in a bipartisan way, and part of that was because the folks representing oil producers, there was a part in there for them, and the idea there was they would use this injection of CO2 to get more oil out of the ground. Well, that kind of self-defeating. And so I'm not terribly optimistic about that. What I am optimistic about is solar power becoming really, really cheap, wind power becoming really, really cheap. And both of those technologies are being built out, you know, year after year. And, you know, I think it's inevitable. It's a good news story for us here in the West because we have a lot of solar resource. We have a lot of wind resource.
Do any of those processes envision separating CO2 into carbon and oxygen, or are they all pump it somewhere we can't find it?
It's mainly pump it down into rock structures that can hold it. In some cases, they're pumping down into basins where there's oil and it brings the oil back up. Like I said, self-defeating. I think those are the main things they're doing with it.
Mike, as I follow the media and reports and whatnot, there's often talk of tipping points.
Yes.
Where the climate change will reach a cycle analogous to the Arctic, but on a global scale. And then even if we stop, it'll continue. Is that still valid, or where is it?
Yes, I shy away from using the words tipping point, although that is a popular term and a lot of scientists do use that. To me, a tipping point means you get to that point and you can never come back, and that isn't really true. But the Earth will eventually come back. We humans may not be here, but it'll eventually come back. But what I kind of prefer the term inflection point, and a good example of that is the methane that's exists in the permafrost. There's a huge amount of methane that's embedded in the permafrost in the high latitudes in Asia, throughout the northern hemisphere. And at some point, as the Earth warms, you're going to hit a point where the permafrost melts and that methane is released, and that will be an inflection point. It will significantly accelerate the warming to a point that we humans probably can't handle it at that point. We probably won't have any way of dealing with it. So in that sense, it would be a tipping point. And that's probably the most, quote unquote, the most concerning, quote unquote, tipping point out there, the release of methane from the permafrost. So when would that happen? Well, we don't really know. Science is not completely definitive there, but the rough answer is probably at a global warming level of about 5 degrees C, which is within the realm of possibilities of where we could end up by the end of the century if we do, you know, business as usual. That was 4.5 plus or minus 1. So on the upper range of that, then we would be up in that 5.5 degrees C warming level. That potentially could start releasing the methane. And once that happens, you know, I think it would I think it would take us beyond the capabilities of human civilization to deal with. I don't think we could stop it at that point. So in that sense, it would be a tipping point.
Hey, Mike, just some comments.
Yeah.
I appreciate that you shared that in financial terms, right? Both the cost for the solution and the savings, because I have to, somewhere I have to believe, or at least hope, that will catch the eye of those companies. You know, when you're talking in terms of money, that someone will eventually see that and see an opportunity. And even when it comes to renewable energy, you know, there's just that hope when you put it in money terms that it'll catch people's attention. And a couple other things I just saw in New York Times briefing that I get each morning. There was another impact to add to your list, and that was higher temperatures caused by climate change and increased air pollution have raised women's risk of giving birth to premature, underweight, or stillborn children. So that was something that just was out, and I think it was published in the Journal of American Medicine Association. So another impact. And finally, I appreciated the video that you showed at the end. I believe some of the footage of the climate change rally that was in, I believe it was in London. I think I was there for that. It was really interesting. We had planned a family trip, my husband and I, my daughter, and kind of got caught up in that. But it was really great to show my then 11-year-old daughter, young people rallying and calling for change. And I'm hopeful with young folks. I mean, my niece, who is in her late 20s, just told me that she's leaving her current job. She had a choice of two different positions, one in Philadelphia that paid a bit more, and one at a plant-based meat company, Beyond Meat in Southern California, and picked that for the very reasons that we were just talking about when it came to ag. So I'm hopeful, right, that future generations are going to be more mindful and demand some solution.
Those are great comments, Jill, and I can really pick up on just everything you said. First of all, on the hopeful part, people ask me, are you hopeful or not? Well, there are two things I'm very hopeful about. One is the technology, the fact that wind and solar is just becoming cheaper and cheaper, and it just makes good business sense. The second is the younger generation. I get a chance every now and then to talk to millennials on this issue, and they really get it. They really get it. They're enthusiastic about it. They care about it. They know it's going to impact them and their children much more than it's going to impact our generation. So they really get it. And I'm very optimistic about that. Yeah, on the financial aspect to it, I think that's another, it kind of ties in with the technology. It's just going to make sense to get away from fossil fuels and invest in green energy. For example, as product drawdown documents in some detail, when you're replacing a coal-fired power plant, it's actually cheaper to replace it with a solar farm. I mean, just the upfront costs are cheaper per megawatt. And then of course, in the long term, you have those huge savings because you're not paying for oil. So it just makes sense economically. I also like to talk about, in terms of wind power, guess what state leads the country in wind power installation? And the answer is the ruby red, Republican controlled oil producing state of Texas. They are number one in wind power. Why? Well, because it just makes good business sense. They got a lot of wind resource there. They got a lot of land. It just makes good business sense. Farmers love wind turbines. They don't interfere with the cattle. They don't take up much land. Their footprint is pretty small. They have this term called the I don't know. I think they call it the sundial effect. All the cattle line up, line in the shade, and they move around all day long. Stay in the shade and move around. So the cattle love them too, and the farmers make money off them. So it's going in that direction, and that's all good. Thanks for those comments.
I wanted to hitchhike on Jill's and say that's the first time I've seen a really apparently well-reasoned cost-benefit analysis. And that's, I think, could be very helpful to moving this thing forward.
Yeah, the fact that there's huge subsidies that are out there that could be tapped into. Now, that would be one of the most difficult things to do. I'm sure it is, because you've got a whole phalanx of high-powered, high-paid lobbyists from the oil industry, and you've got a lot of members of Congress that are in the pockets of the oil industry. That's a tough nut to crack, but that's kind of the direction we need to go in.
Yeah, but a 3-to-1 kind of payback in a reasonable period of time is pretty impressive.
Absolutely. Absolutely. And that's a big part. Yeah, Chowder has a whole slew of, economists on their staff. They've done all these careful analyses. So it's all pretty good. I'm sorry, it didn't come through on the web today, but do check it out. It's drawdown.org. Spend some time there and you'll really learn a lot about the technologies.
Yeah, thank you, Mike. It was great. And our mate ROV competition, which we had to cancel the season this year, obviously, but it all focuses on students' engineering solutions to global problems. And we have a whole mission wrapped around climate change. And I would love, I know you're recording this. I don't know if it's appropriate, or you probably got presentations recorded. I'd love to share that with the students, the global mate competition community, because I think it's
absolutely
really great points. You've organized it so well, and And I'd love to be able to get that out as a resource.
Absolutely. In fact, I've got for everyone, I've got a YouTube channel. It's called Climate Change Matters with Mike Clancy, I think, something like that. Just go on YouTube, search for Climate Change Mike Clancy. You'll come up with that. And I've got 3 presentations on there already. I'll put this one on there as well. And so poke around on that. You know, each presentation is like an hour or so. There's a lot of some of the same material. Some have different focus, but Jill, you're certainly welcome to tap into that and use that.
Thanks, I appreciate it. Thank you.
I'll share with
So
you all.
Mike, that was a very stimulating and very well done presentation. And I certainly appreciate you doing it and taking the time
Thank
and
you much.
being our test guinea pig for Zoom. So thank you so much, everyone, for attending. This was a fun experiment. Thank you to Jim for suggesting it. And if you have any feedback, we'd certainly love to hear it so that we can keep making these presentations as powerful as this one. So thank you very much, everyone.
Thank you, guys.
Thanks, everyone.
Okay.
Attention.
Thank
Good to
you.
see you, Mike.
Okay, thanks.
Take care. Bye.
Bye.
Aye.